Welcome back, and now we're gonna get two more tests for our series convergence toolkit. The first one is going to be the ratio test, and you'll see the root test is nearly identical. This is going to help us to determine convergence and divergence actually too. So for the ratio test, all we're going to do is look at the limit of the absolute value. Okay, so notice that these are here. We have to have absolute values in there. And then we're just going to take the ratio of consecutive terms of the sequence. Okay, if we look at the ratio of those consecutive terms, specifically the next one over the current one, and those are equal to L. If L is a number that is between 0 and 1, then we're going to say that this associated series is absolutely convergent. Okay, so we actually get a little bit stronger of a condition. And again, if it is absolutely convergent, it is convergent. Okay. If L is bigger than 1, then it's going to be divergent, and then L is equal to 1, the ratio test is inconclusive. Now, I used to go through and do a big long proof of at least case 1, but that just ends up confusing people and being a time sink, so I'm just going to say look at pages 734 and 735 and really take your time and wade through those proofs. They are rather useful, but we don't necessarily need to spend time in the videos on them. The idea here, and you might have gathered just based on these ranges of L, is that you want to compare to a geometric series, and so you end up using comparison test in the proof here. So that's kind of a neat little thing. Okay, so ratio test, you take the ratio of consecutive terms, and then if L is within a certain range, then you make a conclusion. If it is inconclusive, then you have to do more testing. That's all that means. More or different tests. Okay. The root test, very, very similar, but you're just looking at the nth root. So this one, you really need to have, like, an needs to be like something to the nth power. Okay, so that's really the only reason you'd use the root test. Ratio test will work in that case as well. It just so happens that the root test is a little quicker. And so if L is between 0 and 1, again, absolutely convergent. L bigger than 1, divergent. And then 1, it is inconclusive. Okay, so I want to get to some examples because that's where we really want to spend our time together. Okay, so in the first example, we have just cosine of n pi all over n factorial. Okay, so we want to figure out which test to use, and your gut might say, well, there are no powers of n, so why do the root test? Let's do the ratio test. Okay, so we're going to try the ratio test. And so with this, I'm going to look at the limit as n goes to infinity of the absolute value. It's going to be a ratio. Okay, so it's going to be cosine of n plus 1 times pi all over n plus 1 factorial, and then cosine of n pi all over n factorial. Okay. And so now we might have to play with these things just a little bit, and we might have to remember our definition of factorial. Just as a recap, n factorial, this means n times n minus 1 times n minus 2 dot 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 all the way down to 1. Okay, but if I play with this, again, this is going to be, for cosine, we're doing multiples of pi, right? What are the multiples of pi for cosine? I think they are just plus or minus 1, and when I do the absolute value, right, they're just going to wipe out. So congratulations, we have simplified our life considerably. Okay, so it's either going to be plus 1 or minus 1, and it'll wash out in the absolute values. Okay, so we're going to have the limit as n goes to infinity, and just rewriting this, this is going to be n factorial over n plus 1 factorial. And again, by definition of factorial, this is going to be the limit as the limit of, let's see, this is going to be n factorial over n factorial times n plus 1 if I were to write that out. And those are going to reduce, and the limit here as n goes to infinity is going to be 0, which is certainly less than 1, right? And so then the conclusion here is, therefore, by the ratio test, series n is equal to 1 to infinity, cosine of n pi over n factorial converges. Okay. So here, so that was a fun one. The next one I want to do with you, and then the following two I want you to do on your own. Okay, so for this one, first I think it's maybe a little prudent to just write this a little bit differently. If I were to write this, so split up the exponent, this would be the same as saying 1/3 sum n is equal to 1 to infinity n to the n over 3 to the third all to the n, which is the same as saying 1 over 3 series n is equal to 1 to infinity of n over 27 to the n. Okay, and now here, the reason I did that is because I have an exponent, so I'm going to use the root test, right? So I'm going to look at the limit as n goes to infinity of the nth root, absolute values I should say, of n over 27 to the n. Well, okay, surprise, surprise, root and exponent are going to wipe out when I do the limit of this. That's going to be infinity. It's going to approach infinity rather, which that's certainly bigger than 1, right? So then as a result here, and say therefore by root test, series n is equal to 1 to infinity n to the n over 3 plus 1, or 1 plus 3 to the power of 1 plus 3n diverges. And boom, done. Okay, for the next two, I want you to pause the video and try them out. So this one, again, maybe it's prudent to write it out first a little bit or condense the notation. And the second one, that one you might have to scratch your head a little bit on. Okay, but I think everything is there for you. Resume the video when you're ready to see the solutions. And here are the answers. So in the first one, all I did was, I did the ratio test, I just wrote it out a little bit differently, and then I multiplied by the reciprocal, just to save myself some time. Got that the limit approached 2/3, so that meant it was converged by the ratio test. And this recursive sequence, be careful with these. These are really interesting problems, because it's usually the ratio test in disguise. If you end up dividing both sides by an, then you get this, and if you look at the ratio of those, then it's 5/4, which is bigger than 1, so it's divergent. Okay, so we will get some more practice with this, all this in class. In general, I find that the ratio test is a bit more useful than the root test, but the root test does have its times too. So be on the lookout for both of these, as well as the alternating series test and making use of absolute convergence when possible.